So today I plan to cover in the first section GNNs, graph neural networks, and large language models, running those on IPU and specificities of those things. So as a quick reminder, the IPU is different from GPUs in the way we implement parallelism and memory access. And this is important for GNNs, for example, because with the faster, larger SRAM and MIMD processing paradigm, we can be more efficient when running operations that are important for graph neural networks, for the message passing portion of the model, specifically the gather and scatter operations. And I'll share some benchmarks on the following slides. So the structure of the entire system will be important more for the large language models. So I just want to mention here, again, as a quick recap from the previous sessions, that each IPU, each processor is put in a blade, which we call Bow 2000 IPU machine. It has 4 IPUs connected together with IPU links and forming torus in the rack. A rack will be hosting 64 IPUs, and we call that system a pod 64. So the links would wrap around the rack, closing the torus in a pod 64. And for larger models, larger deployments, we can go up to pod 128 or 256, which would be, for example, 4 racks with 64 IPUs each. So this topology will be important for the LLM explanation. The bandwidths of the links are also something we optimize for when mapping a model to the IPUs, to a system with IPUs. So IPU links are pretty fast. Each link is 64 gigabytes per second. And then the gateway links are slower. So we want the bulk of the frequent reductions or collective operations to happen within the rack, within the pod, as typical for scale-out systems. So in terms of the graph neural networks, back in 2022, Graphcore research team has worked on the OGB, a large-scale challenge organized by Stanford. And out of the 3 segments of the contest, Graphcore scored the first place in 2 for the graph level prediction and for the link level prediction cases, which the first one was small molecules and the other was knowledge graph and link predictions for that. And overall, we've seen some good feedback on GNN support, including from the PyTorch geometric authors and active users. PyTorch geometric being the framework of choice for multiple research works in the domain of graph neural networks. So, and we want to support PyTorch geometric efficiently to enable these speed ups that engineers can obtain on IPUs by faster gather-scatter operations on top of PyTorch. So we have worked to enable PyTorch geometric as a library for graph structured data overall. And it's easy to get started considering the ahead of time compilation requirements. As I've mentioned yesterday, the compilation on IPUs needs to encompass the entire graph from beginning to the end, including the backwards pass. And that means that the shapes of the tensors need to be known ahead of time. And we can do that by padding the tensor, the batches, and applying some other techniques like packing. We can benefit then from memory optimization and better communication across the cores, across the devices, and end-to-end optimizations of the graph. So how do we enable this fixed size requirements for the tensors, including the modal inputs? Typically for small graphs, Pareto geometric batches creates the batches of the input samples by putting them, say, for batch size 3 in adjacency matrices as shown here. So for example, this small graph, say molecule number 0, its adjacency matrix will be put in the top left corner, and then disconnected molecule, but still put in the same larger matrix, would be number 1 and then number 2, and so on. Give a fixed number of samples per batch, we can see that the sizes of these matrices will be different potentially, because every molecule, every small graph will have a different number of elements, nodes in it, and this will not work as expected on the IPUs because we need fixed sizes of the inputs. So in order to get there, we can do a few things. The simplest one is making the sizes of inputs fixed by padding all the input mini batches to a fixed size. For example, as shown here, there will be a padding small graph, a padding molecule that gets the size of the matrix to some maximum size that will be fixed across all the batch size 3 inputs. Some padding molecules, some paddings will be small, some will be large. So there will be some inefficiency in this approach, but we can achieve the fixed size requirement for inputs easily using just padding, and then the message passing in PyG just works. And as I said, we will need to mask the padding small graph in the loss computation. So we just reject the last piece in the last element in the loss vector. And for Pareto geometric on IPU, we have built a set of components to enable this fixed size inputs. The data loader shown here is an example with the ability to fix the number of nodes and edges, and well, given a batch size of 10, for example. So it will pad each mini batch to this fixed size. And padding graphs, these molecules that do not exist, be ignored in the loss by just this vector operation, throwing away the last element of targets and computed predictions. Another technique that aims to improve the efficiency of the computations and reduce the size of the padding graphs is called packing, and it enables mini batches to be different sizes. up to a certain maximum size of the adjacency matrix as shown here. For example, for smaller graphs, as in mini batch 1, we are able to fit 4 molecules in a mini batch. For larger molecules, it will be only 3. And mini batch number 3 has 5 relatively small molecules fitting in the sample, in the batch. So we are able to thus reduce the padding. If you remember, the padding molecule, the padding graph was quite large here. And we are now using a computation more efficiently with packing. And there is a paper discussing packing. We've done that for language models like BERT and also for graphs. And there can be some other operations that are dynamic, but not obviously dynamic. For example, self loops in some graphs that can be enabled in the graph convolutional layers. This happens to be a dynamic operation. And a way to get around with that is adding self loops during the data preparation as a transform, which makes the tensor shapes fixed before the compilation. And another way is masking for different sizes. If you want to throw away, say, specific nodes from the loss, then instead of selecting as shown here by the mask, you can use the torch.where operation and set the loss of the unwanted nodes to a small value, so it does not contribute to the final gradients in the training. The PyTorch geometric sits at the level of stack similar to PyTorch, so it's on top of the Poplar SDK, which incorporates PopTorch and other layers of stack that are used when compiling the graph for IPUs. And specifically for PyTorch geometric, we have enabled a set of optimizations at different layers of the software, starting from the layers and examples optimized for IPUs that are important for PyTorch geometric. So there is a set of layers verified and optimized that you can use out of the box. Data loaders that enable efficient batching of fixed size inputs. And at the SDK level, many of the layers map, as I've again mentioned yesterday during the porting Poplar deep dive, map to different operations in PyTorch, in Poplar libraries. For example, we do that for the gather scatter operations. And the performance of those operations is something that I will cover in a couple of slides down the road. The gather and scatter operations are important and used for the message passing in GNNs. So, and just as a reminder here, as a quick recap, if you're given a graph with, say, 4 nodes and edges with some values, vectors, associated with each node and each edge, then the message passing would aggregate first the messages given the embeddings for the nodes and the edges, as shown here, the phi function. So it will compute those messages and then aggregate those using maybe a mean or another function to produce the updated embedding of each node, including the target node x1 in this case. The operations that are typically used for this gather and scatter for the message passing for the two stages are the gather and scatter operations. Scatter reduce, maybe scatter add would be typical cases. And we have benchmarked those operations on IPUs, comparing those to A100 GPUs. Given different sizes of inputs and outputs of these operations. The results are shown here for the scatter add operation with a scatter plot on the left and a smooth surface on the right. So it is the same set of data, just shown slightly differently. The conclusion from here is that for smaller sizes of inputs and outputs in this corner here, we are seeing a speed up of about 16x for this specific operation. And then for the larger, we are on par with A100s with some spectrum in between. And this speed up is important for GNNs for the aggregation. And similarly for the gather operation, the speed up are up to 8 times versus A100. So overall, GNNs tend to run faster on IPUs. The reasons behind it are higher memory bandwidth and finer grained parallelism, with all the threads being independent from each other. And then the communications within the chip, all-to-all kind of communication patterns are also enabled by the IPU fabric that we have, which is also fast. It's 11 terabytes per second aggregated bandwidth. And as a case study, Varuni will show during the hands-on session later today the SHNET running on the IPUs, and SHNET is a part of our public examples. It's a model that is used in computational chemistry, comes from this domain of machine learning. In this case, we're using the QM9 dataset of molecules and trying to predict the HOMO-LUMO energy gap for each molecule. The structure of this data set is as follows. We have 3D coordinates of each atom in the molecules. And for each atom, we have the atomic number in the Z variable of the data structure. And then Y is a set of regression targets, something we want to predict. We will be predicting only one of the targets, which is located at index 4, which is the HOMO-LUMO gap. And some sample items, or a single item is shown here. So in this case, the molecule contains 13 atoms, and the positions of those are put in this pos variable here. Now, the edges between the atoms in this representation and in this model overall are inferred from the positions of the atoms, so that the atoms that are close enough to each other would have an edge between them, and they would interact, pass messages through this edge. Now, if we're trying to load a patch with the standard data loader, say batch size 4, we will see that it's different sizes for different samples, for different batches. And in order to execute our ahead-of-time compilation that is required for IPU, we need to make sure that the batches are fixed sizes. We can do that by, for example, running with batch size 1 and padding to a fixed size. So you will see that now we have a limited number of nodes in the item, in the batch here. Some molecules will have a large padding fictional graph added to each. So instead of that, we can run with a larger batch size and pad that larger batch size to some fixed number of atoms in the entire batch size, which is done in this case. So we are using this custom fixed size data loader, which is a part of the IPU version of or wrapper of PyTorch geometric. And when computing the loss, we throw away the padding values for the predictions and for the targets. And if we visualize the batches produced by this data loader, we can see that now they are all fixed sizes in terms of the number of atoms in each batch. As mentioned yesterday, we can also apply some optimizations. We can do a loop on the device here, which is set by this device iterations option of PopTorch. We run with a number of gradient accumulation happening per each computation, and the learning rate and number of epochs are also among the parameters of the execution. So the main model from creation to compilation is shown in this extract, in this script. So we build the interaction graph, k-nearest neighbors based, which determines basically how the edges are structured given a molecule. And then we build the SCHNET model, put it in a trainable regime, and use this training module wrapper around the model to be able to run the model going forward. And we define the optimizer using the PopTorch version of ADA with weight decay and the wrapper of PopTorch as well for the model. And after that, we have compiled the model outside of the training loop. Let me go back and show this line number 12, which takes some data that should be of the target size in terms of tensor dimensions. And with that, we'll leverage the binary created during the compilation and run the training loop as shown here. So the training model would, the call to this training model will execute the gradient step and output the loss for this batch, which will be a vector containing losses for all the molecules in the mini batch, which we then store as a mean across the molecules in the mini batch, and we output it to some tracking solution, maybe a list of dictionaries with epochs, steps, and loss values. And we can then follow the trajectory of the loss, visualizing it in the same script or somewhere outside. So we can run this example today, and I'm happy to answer any questions before we switch to the language model portion. Let me see how we're doing on time. Okay, I have 15 minutes or so. So in terms of the large language models, we have two ways to run those on the IPU-based systems. One way is by using the Optimum Graphcore library, which is built by Hugging Face and Graphcore teams working together. And the Optimum Graphcore is an easy way to leverage a lot of models in the Hugging Face repository while doing a small number of changes to the scripts, the standard scripts when running Hugging Face models. The main changes are shown on this slide here. So we, instead of transformers, we use Optimum.Graphcore module, and we use that for the classify here. Similarly, we use when building the trainer class, IPU config, IPU trainer, and IPU training arguments instead of the generic ones here. And IPU config is an additional class with a configuration of the system for the specific model. And then you add this IPU config to the trainer class to run the model. So for a lot of models, those examples exist and run successfully, as shown here for, well, quite a few in different paradigms, different use cases. And also among the examples in the Optimum Graphcore repository, you will find several models and cases for things like question answering and speech and classification and summarization. So I would encourage you to take a look at that if you're interested. And specifically, the notebooks section in that repository is also quite helpful. And here you can see examples that train external models that are not a part of Optimum or transformers, and show how to pre-process the data and fine-tune a pre-trained model on a question answering data set, and so on. And each of the examples would have either a README file or it would be a notebook with detailed instructions and a discussion there. And one of the examples that we have in the main examples repository inside the Graphcore organization on GitHub covers the GPT-3 175 billion model, which requires a pod 256 to run. And here I plan to cover the main principles that we used when executing and building this model and running, porting this model to IPUs. So the framework that is used for this implementation is called PopXL, which is a portion or a part of the popular advanced runtime for part with some additional tools to run distributed or data parallel, tensor parallel computations with better control over the mapping of the graphs. Again, just as a reminder, the data parallel regime is when you have several replicas of a model, and each replica is seeing maybe a subset of your training data. And then as you train the model, each replica works independently on a batch or a set of batches. And after a set of batches, it would do a reduction of the gradients across all the replicas so that you end up with a shared set of weights before continuing with the next set of batches to run. And with this, you can train your model faster because of the additional parallelism running across several replicas. But you need to be cautious of the effective batch size, which can affect your convergence in some cases, and of the overhead of executing these reduction operations of these collectives, because it will take some time compared to just a single replica where no reductions are required. Another parallelism that is important for very large models, and is called tensor parallelism. It was described in several papers. One of the first was the Megatron paper, which implements one-dimensional tensor parallelism, which I will describe on the following slides. And another thing that is typical for GPUs, and we used it for the IPU implementation of GPT-3, is what we call phased execution, where you stream a portion of the weights from your external memory to the compute. You execute an operation on that set of weights. Maybe you stream your batches for a given layer, and I should say activations for a given layer through the device, and leverage the preloaded weights for that stage. And then you stream out the activations that you produce after this phase. And this process continues. So this phased execution allows you to not load the entire model in your, say, SRAM, but it adds computation, adds communication overheads to your execution. In terms of the tensor parallel operations, it is helpful to distribute matrix multiplications across multiple devices, multiple IPUs in this case. And in this regard, it helps reduce the memory pressure, because the operations, when distributed across more than one chip, require less memory to store, say, the weights of the model. And in some cases, these help to reduce the memory bandwidth pressure when loading the weights or activations from the external memory. So this operation, when we are multiplying one matrix by another, say, this would be our activations from the previous layer, and these would be the weights of the current feed-forward layer. We can represent it by, well, segments of matrices as shown here. And we will have two options when distributing this computation across, say, two devices. So if we say that the dimensions of the two matrices are as shown here, and M for X and MK for A, then the final result using the portions of the matrices will look like this. Each matrix can be computed kind of separately in parallel with each other. And based on that, we can consider two options for the parallelism. We can split the matrix A column-wise, as shown here, and one slice of this matrix will reside on, say, one device number 0. The other slice will reside on device number 1. Then we can compute portions of the resulting matrix as shown here. So it will be an independent computation for left part and for the right part, that after will need to be concatenated with each other. So we end up with shards of the resulting matrix. And in order to produce the final result, we'll need to do an all-gather operation to pull together the partial results so that a device would contain all of those. The nice thing about it is that each shard of the resulting matrix is complete, and if we need to apply a non-linear operation like GLU, for example, we can do that independently on device 0 and device 1 here. Another option of doing tensor parallelism, of sharding the weight matrix, is doing that row-wise. And in this case, we will unfortunately need to do a similar kind of sharding, or follow map the similar chunking to the matrix X as well, to keep the number of dimensions correct for the matrix multiplication operation, so that XA, or this left portion of the matrix X, will be compatible in terms of dimensions with A sub A matrix, so that the inner dimension is the same for the two. And the result will be as shown here, with one component being only a partial result of the full size of the n by k in this case. And in order to produce the final output, we'll need to add the two matrices, potentially residing on different devices. So if the left side of X is put on device 0, and the top part of the matrix A is put on device 0, then this component will be produced on device 0, and vice versa. The second component will be produced on the other device, the device number 1. So we need to sum up these partials to produce the final output, and this will be an all reduce operation, reduce sum in this case. The good thing,
there's a question on the chat.
what is the maximum size of each shard? The maximum size of each shard depends on the number of devices that you split your computation across. For example, if you're doing the parallelization, if you're running tensor parallel across 2 devices, then the M dimension of the the k dimension of the matrix will be divided by the number of shards that you have. So there is no maximum in this regard, but you will need to be careful to leverage your memory appropriately, so that you do not run out of memory, for example, in some cases. Let me know if that is what you meant to ask, if that answers the question. Thanks for the question. The simplified feed-forward layer of a transformer would look something like this. Typically, you will have some activations from the previous layer, like attention, going through layer norm operation. Then there will be a matmul with the weights for the first feed-forward layer, nonlinearity applied after that, and another matmul with the second set of weights for the second feed-forward layer. So this is the option, or what it looks like with no tensor parallelism. And the sizes of the matrices are shown here, with S being the sequence length, H hidden dimension, and then Y the first feed-forward layer. So it's typically moves the dimension of the activations from H to 4 times H. So this is a huge matrix potentially. The activations after that will be this size, and then we project it down to the H dimension, and the final output will be of the size S times H, as we had it in the beginning of this layer. Now, if we run tensor parallel with 1D, one-dimensional tensor parallelism, as it was described previously, we'll observe that now the weights are split across the devices, which we will call the device set A and device set B, because each, well, it can be not a single device, but more than one device in each tensor parallel group. And the dimensions of the weights are now divided by the number of devices in the tensor parallel group number 1. For example, if we are running with a number of devices TP1, then each device will have only a slice of the weights of this Y matrix. And the matmul here on each device will consume the activations X from the previous layer after the layer norm that are broadcast to each device. So you will have X matrix duplicated across all the devices here. And then on each device, we'll produce a slice of the activations here. And the good thing is that now we can apply this nonlinearity independently on each device. And with that, we can avoid any additional collective operations in this pipeline. Because as we use this row-wise sharding of the matrix Z, we will be able to produce a matrix of the full dimensions of the entire S by H size on each device. It will be just a partial matrix as I shown here. So wanted to get back to this slide here. The first portion of the feed-forward set of layers in the transformer will be producing this set of tensors and then applying the GLU independently to each segment of this matrix. And then the second netmul will be producing partials as in this expression here. And then we'll need to summarize those partials across the devices with the all reduce operation during the forward pass. And during the backwards pass, this becomes a no-op, and the all reduce is used for the gradients, while on the forward pass, this all reduce does not exist. So it becomes a bit more involved, and this is what was described in the original Megatron paper. Now, there can be a challenge that the matrices are still large for the local memory of the devices, and one needs to apply to shard the activations across more than one device as well, and that will become what's called two-dimensional tensor parallelism, as shown here, which introduces an additional collective operation and all reduce across the tensor parallel devices on the second dimension. In this case, well, the weights are distributed across, well, each device will contain a slice of the weights sharded not only by the columns, but also by rows. And the multiplications will be producing smaller matrices. This additional all reduce in between. And with that, you will end up with a similarly sharded set of activations at the end of this pipeline. So on a PODSIC 256, we have analyzed the different configurations that can be used to map the models, so the GPT-3 specifically, across the IPUs. And given the bandwidths of the connections of the IPU links and gateway links across the pod, we decided that the best configuration will be to put a replica of the model inside the rack, because within the replica is where all the collective communications are happening during the backwards and forward pass, most of it at least. And then the gateway links, which are slower, will be taking care of the data parallel communications that are less sensitive to the bandwidth of the links. And the 2D parallelism needs high bandwidth, tensor parallelism, I should say, high bandwidth between the replicas, especially the second dimension of the tensor parallelism, because in that case, you are working with matrices that are 4 times larger in size because of the first feed-forward layer there that increases the dimension of the matrix. The configuration that we have chosen is shown here for the TP tensor parallel 2 groups. Each group is 8 IPUs distributed within a rack, as shown here. So each device in this group will have a slice of the weight matrices. And another dimension for slicing the weight matrix will be what's called tensor parallel 1 groups. So the group number 1 will contain devices shown in red color here. So with the stride of 8 in this case, and group number 3, for example, will be devices number 2, number 10, and so on. So and then with this configuration, the all reduce operations leverage the bandwidth of the IP links efficiently. I think this is kind of the main thing, the main section, main set of points that I wanted to convey here.